I ask you a question. If I replace all raw pointers in my code with smart pointers, will the program be safer? The answer is yes. Will the code be cleaner? Most likely yes. Will the performance be better? The answer is not necessarily. Even in some cases, your program will become significantly slower, slow enough that you can directly measure the difference. Today, we will talk about something that many people are reluctant to admit. Smart pointers are not always smart. In modern C++, smart pointers have almost become a kind of political correctness. You must have heard these sayings. Don't use raw pointers anymore. Everything is RAII. Use unique pointer as much as possible. Use shared pointer only if you have to, and use shared pointer only as a last resort. These sayings themselves are not wrong at all. Smart pointers can indeed automate memory management, no more manual delete, reducing memory leaks. And they are exception safe. Even if the function throws an exception halfway, the smart pointer can automatically destruct, avoiding resource leaks. And they have clear ownership semantics, such as the exclusive ownership of unique pointer, the shared ownership of shared pointer, making the code logic easier to understand. Many people begin to subconsciously think, the more smart pointers are used, the better the code. The problem lies right here. What is a smart pointer? It is not magic. It is essentially a class, a template class that encapsulates a raw pointer. It is just like a class we write ourselves. It has constructors, a destructor, and member variables. And all of these will generate extra machine code after compilation. Even the seemingly zero-cost unique pointer has hidden instruction overhead in certain scenarios. That is to say, you think you are using a pointer, but actually you are using a whole set of encapsulated logic. This set of logic brings safety and convenience, but it inevitably brings extra performance overhead. Many people think that unique pointer is a zero-cost abstraction, that using it is no different from using a raw pointer and the performance is exactly the same. But that is not the case in all situations. There are two scenarios where its cost becomes magnified. The first scenario, the cost of move semantics. Let's look at a very simple piece of code. Every time this function is called, you must pass a unique pointer, and because unique pointer has exclusive ownership and cannot be copied, it can only be moved. This means that each call triggers a move construction and a destructor of the old object. Some might say, isn't a move operation very lightweight? Indeed, the cost of a single move is very low, but if this function is called at a very high frequency, for example, in a loop that executes hundreds of thousands of times per second, the cumulative overhead of these seemingly minor move and destructor operations becomes very significant, and can even be directly captured by performance testing tools. The second scenario, limiting compiler optimizations. Because unique pointer explicitly expresses the semantics of exclusive ownership, the compiler must strictly obey this rule and cannot optimize arbitrarily. This sometimes leads the compiler to become more conservative in its optimizations, especially in alias analysis. To give a concrete example, if you use a raw pointer to point to constant data, the compiler can directly cache the data in a register, and when accessing it repeatedly, there is no need to read memory again. But if you use a unique pointer to point to this constant data, because the compiler must guarantee the exclusivity of ownership and cannot be sure whether the pointer will be modified, it will not perform such register caching optimization, resulting in a memory read every time you access the data, increasing the time consumed. This difference in optimization becomes noticeably magnified in high-frequency access scenarios. If unique pointer is only potentially costly, then shared pointer is truly expensive. First, reference counting. Inside every shared pointer, there are two core parts. One is a raw pointer pointing to the actual data, and the other is a pointer to the control block. Inside the control block, besides the reference count, there's also a weak reference count used to support weak pointer, as well as a deleter and an allocator. The core function of the reference count is to record how many shared pointer instances are currently sharing this data, and the weak reference count records how many weak pointer point to this control block. Every time a shared pointer is copied, the reference count is atomically incremented by 1. Every time a shared underscore PTR is destroyed, the reference count is atomically decremented by 1. When the reference count drops to 0, the underlying data and the control block are finally freed. This means that every time you pass a shared pointer, every time you copy a shared pointer, you are performing extra memory operations. And memory operations themselves are among the time-consuming operations of the CPU. Especially when memory fragmentation is severe, the allocation and deallocation of control blocks become slower. Second, the most lethal part, atomic operations. In a multi-threaded environment, multiple threads may operate on the reference count of the same shared pointer at the same time. For example, one thread copies a shared pointer, count +1, and another thread destroys a shared pointer, count -1. To ensure the thread safety of the reference count, the increment and decrement operations on this reference count must be atomic. Atomic operations mean that the CPU needs to execute a lock instruction establishing a memory barrier which causes the CPU pipeline to stall and prevents subsequent instructions from being executed in parallel. At the same time, when multiple threads operate on the same cache line, it also causes cache contention, which is what we often call cache line bouncing. One thread modifies the reference count in the cache line, causing the cache lines of other threads to become invalid, requiring them to reload from memory, which greatly wastes CPU resources. Finally, memory layout and cache issues. A shared pointer typically involves two separate memory allocations. One is the control block, and the other is the actual data. A raw pointer only needs to point to one block of data memory. That is to say, when using a raw pointer, the memory layout is compact. When using a shared pointer, the memory layout is split into two independent blocks of memory, which may be located in different positions in memory, possibly not even in the same cache line. As a result, accessing the data requires one extra memory access. First, through the control pointer of the shared pointer to access the control block, then through the data pointer of the control block to access the actual data, and at the same time leads to worse cache hit rates. The CPU cache loads data in units of cache lines. Two independent blocks of memory are unlikely to be loaded into the same cache line. Frequent cache misses will greatly reduce the execution efficiency of the CPU. This is very fatal at the CPU level because the speed of the CPU accessing the cache is dozens or even hundreds of times faster than accessing memory. A single cache miss may require dozens or even hundreds of CPU cycles to complete the memory access. Let's look at a very typical scenario so everyone can intuitively feel the difference. For example, a loop that creates a shared pointer in each iteration and then uses it. What is actually happening in each iteration? First is memory allocation, allocating the foo object and the control block. Then is control block initialization, setting the reference count to 1. Then come possible atomic operations during use. After the loop ends, pointer goes out of scope. The reference count is decremented by 1, which is also an atomic operation. The reference count becomes 0, and the control block and the foo object are freed, which are two memory deallocations respectively. With this entire set of operations, each iteration has multiple memory operations and atomic operations. Now compare this with the case of using raw pointers or directly using stack objects. What happens here? There is no memory allocation at all. Stack objects are automatically managed by the compiler, no manual allocation and deallocation needed. The allocation and deallocation of stack memory is just moving the stack pointer, which has almost no overhead. There are no atomic operations at all. The object's memory is on the stack, and the cache locality is extremely good. Stack memory is usually loaded into the CPU cache first. The CPU can directly read data from the cache, and the execution efficiency is extremely high. Having said this, some people will surely ask, should we still use smart pointers? I'm not saying don't use smart pointers. On the contrary, they are very useful and indispensable in many scenarios. First, when the lifetime of an object is complex. If an object may be referenced from multiple places and it is not known when it should be released. For example, a UI component that may be referenced by multiple containers and the timing of destruction is uncertain. In this case, using shared pointer perfectly solves the problem of shared ownership. Second, when ownership is unclear, and in team collaboration it is difficult to determine who is responsible for releasing the memory, making memory leaks likely. For example, when multiple people develop a module, someone creates an object, someone else uses the object, but no one is explicitly responsible for delete. In this case, using smart pointers can avoid memory problems caused by unclear responsibility. Third, when exception safety is required. Exceptions may be thrown in the function, and manual memory management easily leads to leaks. For example, if you new an object in a function and then exception is thrown, the delete statement cannot be executed, resulting in a memory leak. Smart pointers, however, will automatically destruct when an exception is thrown, avoiding such leaks. Fourth, when passing objects across modules. When passing objects between different dynamic link libraries, ownership is difficult to manage. Using shared pointer ensures that the object is destroyed only after all references have been released, avoiding dangling pointers. Modern C++ is very powerful. It provides us with many efficient and safe tools, but the power of these tools is premised on you truly understanding them, understanding their underlying implementation, understanding their costs and benefits, so that you can truly use them well rather than being enslaved by the tools. If you enjoy this kind of content that debunks C++ common sense and digs deep into low-level principles, welcome to subscribe. In the future, we will talk about more easily misunderstood knowledge points in C++. All right, that's all for today. See you next time.